Hello, everyone. I think I'm live. I can't tell now. I'm hoping I'm live. Oh, there we go. I think this is working. So I'm going to just transition to here and we'll see what happens. Hello. So if you can hear my voice, please just comment saying we can hear you, Mr. Dharma. I know last week when I tried to do the last live stream, I had a bit of technical difficulties, and let's hope I don't have that kind of issue. Perfect. So let me just recap on some really important properties of graphs. So we sort of discussed this last time, but I don't think I did a great job. So we'll just quickly just check in. We've got the idea of symmetry, x-intercepts, symmetry, x-intercepts, turning points, and then so these are graph properties, right? And then these two are function properties. They're the domain and the range. Depending on what I set the domain and range, I can create a different situation. Okay, and you're like, Mr. Dharma, please clarify. So I'm going to draw a rough parabola. Okay, and it's not going to be the best parabola in the world. All right, okay, here's my parabola. Now, what's really important is this function has symmetry through the middle, has x-intercepts, just one here, has a turning point also here, but the domain and range is solely dependent on what I want to look at. So if I only want to look at this part of this graph here, between 1 and 4, then 1 and 16 becomes my range, and 1 to 4 becomes my domain. And that's sort of the kind of thing I was trying to get at last time, but it was really hard for me to do without a whiteboard. So the domain is what you want to use, right? What x values you can plug in, and the range is what y values you get out. And so if I only wanted the blue part, I'd just say the domain for this function, f of x equals x squared, is my model. I'd say my domain is from 1 through x through 4. And I'd say my range is 1 through y. So 1 to 4 is my domain, and 1 to 16 is my range. Okay? As for what the red graph is, the red graph, the domain and the range, well, the domain for the red graph is all real numbers, and the range for the red graph is positive. But that's not what I was looking at, right? I'm just looking at a small section of that graph, and that's sort of what I wanted to just remind you of. Okay. If you have questions, pop them in the comments now, but I'm just going to now move on to the next few sets of graphs. Okay. Now, this next one, exponential graphs and functions. All right, exponential graphs and functions. They are of this form. F of x equals the standard form is base to the x. Okay, these are very common. Base is a fixed number. X variable. Okay, so how do these look? Well, let's look at a simple example. We've got 2 to the x, we've got x, and we'll try to fill out what this function is. So when x is 1, 2, 3, 4, 5, 2 to the power of 1 is equal to 2. 2 to the power of 2 is equal to 4. 2 to the power of 3 is equal to 8. 2 to the power of 4 is 16, and 2 to the power of 5 is 32. And so on. I don't have to only have whole numbers here, but this is how I look at what exponential graphs look like. And if you can tell, they grow quickly. And so on a graph, exponential graphs, typically they go through 1 when x equals 0, and they never are negative growth curves. Okay, but you could, if you made the power negative, you could make exponential graphs that look like this, where they shrink. Well, they're called decay curves. Okay, but I'm going to get rid of that one. We don't need that one for now. So that's how exponential graphs work. And so what I'm going to do is I'm going to just quickly plot a few. Okay, so I'm going to say f of x is equal to 3 to the power of x. Okay, I'm going to look at what that looks like. Then I'm going to look at f of x equals 4 to the power of x. What does that look like? What do the numbers mean? Right? By this, how I'm going to draw them is I'm going to draw a little table. But I don't want to do it by hand. I'm going to use Desmos to draw this table for me. And so I'm just going to switch to Desmos so you guys can see. But please just put in the comments if you understand and can hear me and are following along fine. Thank you. All right, so now over here, I'm going to label my x-axis and my y-axis. We'll go up in steps of 1. We're going to get rid of this. Okay. Look at this graph. Okay, this. Oh no. You guys can't see me do changes on here, can you? It's really frustrating. I'm going to just forego Desmos. Perfect. All right, that's really frustrating. So, yeah. So this is what it looks like. If I draw a table, x and 3 to the power of x. Here we go. X is 1. Now let's go with x is 0 first. X is 0, x is 1, x is 2, x is 3. Is 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. Can you see that it grows really quickly? And so if I were to draw this to scale, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then if I had 1, I'm sorry, that's not what it meant to look like. 1, 2, 2, 9, that's fine. But the thing is that by the time I get 327, it's off the graph somewhere. And so exponential graphs become really, really, really hard to draw on exponential graph on normal scales. They become really, really stretched really quickly. And so it's really important. But instead of going to 1, going to 3, it will go to, sorry, I thought this was going to change color. Check this. We'll go through here, and it'll shoot through even faster. And so that's all exponential graphs are. But what about the properties of exponential graphs? Well, the domain and range are the same kind of ideas. So what part of the graph are you going to use, and how much of the domain and range are we going to use? So that's not going to change too much. Symmetry, though, not symmetrical at all, ever. What else? Turning points. None. So symmetry, turning points. X-intercepts for these are very awkward and very rare, depending on the context. Okay? So, because the thing is, exponential graphs don't go below the axis. So typically you don't have x-intercepts unless you move the function down. And then domain and range doesn't change much depending on what you want to use. And so exponential functions are really cool. As long as you know what they look like, they have a few transformations. So, if you have an exponential function, if you plus 2 or plus 3, this shifts the whole graph up 3. If you go like that, just like parabolas, it moves it to the right 2. Okay? And that's how exponential graphs work for us. Okay? So there's either a vertical shift or a horizontal shift. And yes, there can be a scale, but we will talk about that another day. Okay? Every point is scaled up by 4. But I don't want to focus on that so much. I sort of just want to look at the fact that exponentials are not symmetric, have no turning points, and x-intercepts are rare unless some weird stuff happens. And that's kind of interesting for us. Okay. Next graph I'm going to look at is going to look very similar. Logarithms. Okay. The graphs of logs depend on what the base is. Okay. And so let me try something. Log base 3 of x. Okay. This time, if I want to make a table, I do something really interesting. I go, well, this is x, and this is log base 3 of x. But this time I fill out the log base 3 first. And I go 1, 2, 3, 4. And we fill out the x values. If the log is 3, what was the x value? Well, what is the power of 3 that gives me? Remember, this is saying 3 to the power of, if I were to write it out like this, 3 to the power of y is equal to x. So what is 3 to the power of 1? 3. What is 3 to the power of 2? 9. What's 3 to the power of 3? 27. 3 to the power of 4? 81. And in fact, logs and exponentials are kind of the same. But they are on the opposite axes. So a log graph, instead of going through one here, goes through one here typically. And then they only go up in ones this way. So if I were to draw it, it would look kind of like this is really hard for me to draw on a computer, guys. But kind of like that. The opposite direction for how exponentials work. But they grow very, very slowly. Where exponentials up here grew very, very fast, logs grow very, very slowly. Okay, because the next x point is 81, which is so far away, but it's only one up on the y-axis. Okay, but the thing is, the domain, the range, the y-intercept, the domain, the range don't change. The x-intercept is typically 1 unless you change it. Symmetry, none. X-intercept is typically 0, 1 unless changed. Turning points, none. And the domain and the range, once again, they're not a graph property, but they're a function property. So where you want to use the domain and range is what's really important. Okay, so if I only wanted this part here, between here and here, I'd say my domain is from 3 to 9 and my range is from 1 to 2. Okay, but I'm not going to get into the ins and outs of that. But these are called logarithmic graphs. They grow slow. Exponentials grow super fast. Logs grow super slow. Okay, and you're like, Mr. Dharma, is there another kind of graph that we could possibly learn? And the answer is yes. The last kind of graph that I want to show you today is a hyperbola. So here is a hyperbola. Hyperbola is the single, right? Hyperbolae is the plural. So more than one hyperbola become hyperbolae. All right? It's sort of like the same as formula, and the plural is formulae, not formulas. But people get lots of confusion and do weird things, so I don't want us to try and do anything too gnarly. All right, standard form of a hyperbola are functions that look like a over x. Okay, something divided by something else. And in fact, these graphs are kind of very common. We kind of do these a lot, but we've not actually explored them. And these graphs look really weird. But let's do a simple example. I'm going to do y equals 24 over x. Okay. What I'm going to do is I'm going to list off x's and y's. So x and 24 over x. I'm going to start with nice ones. So I'm going to go 1. What's 24 divided by 1? 24. 2. What's 24 divided by 2? 12. 3. 24 divided by 3. 8. 4. 24 divided by 6. 6. 8. And I'm just going to use nice and whole numbers, okay? Because I kind of want to show you something really weird. Okay, so these points, if I plotted them, they kind of look like this on an axis. So 1, 24, 2, 12, 3, 8, 4, 6, and 6, 4. No, that's 6, 4, and then 8, 12, 8, 3 rather, and 12, 2. And so you get this graph that looks kind of like that. But what's weird, right? So this is 1, 2, 3, 4, 6, 8, 12. I know it's not to scale, but you kind of get the point, right? But the thing is, if I copied this table, and then I just pasted, and did something weird, and I just plopped it on the bottom of this, and then if I just changed all of these to negatives, then I get a graph that looks exactly the same as this, but negative. And so I have a graph that looks like this. And so hyperbolas, this is really hard for me to draw on a computer. Right? Hyperbole or hyperbolae, they look like this, where there's a positive part and a negative part. And there's a key word that we're missing that I really want to talk about. Okay, because all the negative part is over here, and all the positive part. So this is all the positive part, and this is all the negative part. And they never meet, but it's two parts to the same equation. All right? And so if we go to properties, domain and range, they sort of stay the same. That's meant to change color. The domain and range, once again, is a function thing, not a property thing. Symmetry, they are not symmetric in mirror lines, but they are rotationally symmetric. Sort of like cubics, right? Because if you flip this whole graph upside down, or spun it around, you spun this graph, if you spun this graph around, let's see if I can spin this graph. It kind of still looks the same. Okay, I know I've drawn really badly, we don't need to bring that up, but you can kind of see that it sort of still looks the same if you spin the graph. So rotationally symmetric, no turning points, x-intercepts, they don't normally happen. What are we missing? Turning points, x-intercepts, symmetry, and domain range. We've done them all. Okay, and there's something I'm missing. And that thing that I'm missing, what I think is really important, is that these graphs have this other property that we haven't explored. Okay, all three of these have this property. Okay, and this property is called asymptotes. That's a very hard word to say. Asymptotes are parts of functions that are really important. So let me draw one of each of these graphs. So here's my exponential. That's my exponential. Here's my log. Right? And here is my hyperbola. Oop. Okay. That last one was terrible. Okay. Exponentials, logs, and hyperboles. They have this special line, which I'm going to draw. You can't see it, so I'm going to try and dot bigger. Okay, here we go. This line here is the asymptote for the exponential. Y equals 0. Y will never equal 0, and so this green line is something that will never be crossed. In the log graph, x is equal to 0 is the asymptote. That line will never be crossed. And for your hyperbola, unless you transform it, y equals 0 and x equals 0, x equals 0 and y equals 0 are your two asymptotes. And they tell you where your graph will not cross over. And so these asymptotes become the third, but they also are symmetric along this line. Okay, and so that might be useful to us sometimes. And so they've got key things about these three types of graphs are they have asymptotes, meaning there's parts of the graph that they will never go past. They all are kind of nice in the sense that they don't have turning points, and their symmetry is kind of different to how other graphs have symmetry. All right. I don't want to do too much more on this. There's a few things that you could do to try and graph these, but the whole point of this session was just to explore what these graphs are and what their properties are. So your teachers will start putting more questions and work on this kind of content for you. And remember to take a break, ask your teachers for help if you need to, and sing out if you get stuck. Are there any questions? I'll wait a couple of minutes, and if there are no questions, I will end the call today, end the stream today. And a lot of familiar faces in this. A lot of people I've taught. Nice. Or are in my class. This is cool. And a lot of year 11s. This is outstanding. Welcome, team. Okay. Well, make sure you talk to your teachers. I haven't received any questions. When will the Desmos student code be given? Desmos will be given, well, your teachers will have uploaded Desmos onto your classroom. So if you're in my class, I've given you a Desmos code to be working on right now. It's been up since about Friday, so you should probably be working on that, Najaya. So your Desmos codes will be on your in how your teacher presents information to you. Okay. Thank you, team. The first exponential was all real numbers for domain. Yes. So unless you restrict it, the domain for exponentials is all real numbers. The range for exponentials is only the positive real numbers. The domain for logarithms is positive real numbers, but the range for logarithms is all real numbers because logarithms, so this graph here, the x value will never be negative unless you change something, right? And hyperbole, domain, and range are the same apart from 0, but that's all how you transform. Okay, guys, I'll catch you later. Thank you. Bye.